Welcome, everyone. Thank you so much for coming. It's my pleasure to introduce Zhongwei Zhou, who is an assistant research professor at the moment in the Department of Computer Science with a joint appointment in oncology through the School of Medicine's Sidney Kimmel Comprehensive Cancer Center. He's also a member of DSAI and the Center for Imaging Science. And he's going to talk about a lot of the work he's done on medical computer vision, language, and ethics for early cancer detection and diagnosis. And I think he'll talk about some of his prior work, but in the interests of highlighting some of his accomplishments very briefly, he's known for developing UNet++, which is a widely adopted segmentation architecture, which has been cited over 18,000 times. He also, his work has received multiple awards, including an ENIA doctoral dissertation award, among others. And we're all excited to hear about the AI that sees cancer coming. So let's give our speaker a round of applause.
Thank you very much for the introduction. It's very glad to be here to present our work. The title will be the AI that developed at Hopkins that can see cancer coming. So what we are talking is see even monthly or yearly before radiologists. Cancer is a topic that might impact many people, many families, and I'm focused on cancer early detection because most cancer, they do not have a very clear symptom, and when it's detected, it's already too late. And if it's too late, the 5-year survival rate will only be 7%. But if we have a way to detect it much earlier, then it's still terrible, but the survival rate will increase dramatically to 44%. Even the patient have the CT for whatever reason, maybe cancer reason, non-cancer reason, doctors will miss the early stage cancer for the 60% of the time. And this is the motivation that we think whether AI can take a look at all this scan and help radiologists to identify the cancer much earlier. I want to start with the successful story about pancreatic cancer. We formulate this problem in a computer vision setting as a 3D semantic segmentation. Basically, you train an AI model to classify each voxel. It's a healthy pancreas, or it's a cancer, or it's a background. And we test this AI on both cancer and normal patients. Here is a quick result. The sensitivity basically means if this patient have the cancer, how many times the AI or radiologist can find it's a cancer. And the specificity also very important to make sure the model or human do not raise too many false positives. And we see radiologists, their sensitivity is okay for the all size tumor. But if you look at the small tumor, less than 2 centimeters, the sensitivity only 33 to 44. And our AI can reach 94% sensitivity while maintain very high specificity without giving too many false alerts. And we group with a number of radiologists, 30 radiologists from different expertise level. We ask 2 pancreatic specialists and 12 general radiologists and 15 radiology residents to do this retrospective reader study to see whether they really cannot see it or not, or they missed it because of the tiredness. And here's the result of the group of radiologists. They, as said, they have a very high specificity, but the sensitivity, we verify it's similar to what report in the literature. It's only 30 to 40 sensitivity. And here is the AI I want to introduce you that see the cancer coming. It can reach almost 30% sensitivity improvement given the similar level of specificity. And we not just ask this AI to look at the current scan, we also ask it to look back to this pre-cancer scan that if the AI can find it or not. And all this scan has already been missed by the radiologist. So we call it a pre-diagnostic scan. which taken 3 to 36 months before the clinical diagnosis. So practically, this cohort of the patient are completely missed, the radiologist completely missed the early cancer in this case. And we want to test the AI on this cohort to see if it can see anything or not. And we found that the AI is able to find the early cancer at least 1 year before radiologist. So you see, you give this patient 1 extra year to get the effective possibility to get the effective treatment. And the sensitivity of the 3 months to 1 year is very high. And if you go down to the longer term, even AI cannot do very good job, because maybe in this kind of a scan, there's no visible tumor at all. And for the reference, I put the radiologist performed here, practically is 0. And this AI not only can tell radiologists there is a cancer, it can also help them localize where it is. So it's more interpretable. So the radiologist can look at this region and decide whether it is true or not. So our AI is a segmentation AI, so it will give the boundary of the cancer. So we make this AI as an assistant tool to give the radiologist not just the CT scan, but also the AI prediction on top of it. So the radiologist can turn on or turn it off. And we reanalyze the performance, the AI plus human, and we find it can dramatically outperform the human alone and also outperform the AI alone. So that's a very nice story to tell. And I want to talk about why our team can can make it, and what kind of challenge we are facing. There are 3 challenges. That tumors are very small, and usually computer vision algorithms, they are not very good at detecting such small object in the image. Second, tumors are very rare. You don't even have enough data to train this AI model. And third, annotating the tumor is difficult because we frame as a semantic segmentation. So the annotator have to give the boundary of these images. And I will introduce our solution to all these challenges. Start with the small tumor detection problem. Let's understand what is the difference between the natural image database and the medical database. In natural image, usually the object is very big and in the center, very obvious, and the AI can detect it for no problem. But in medical domain, most images are in 3 dimensions. So the object of interest in this talk is cancer. It's only 0.0001% of the entire image. So it's more like ask a natural computer vision people to solve this with a Waldo problem instead of find a cat or dog in the image. And I found that even the state-of-art computer vision model or GPT have a hard time to do it, because the cancer is just a few pixels, and there are so many different information that could be useful, but not directly what we're interested. And here is the Waldo, by the way. So that's why in medical domain, people really need to innovate their own algorithm to solve this problem. And the very standard algorithm is called UNet. It has been there for 10 years. It's very widely used, not just for medical domain, but also for computer vision, for diffusion model, generative model, and so on. And in my PhD, I also try to improve the UNet in such a way that to make the UNet be able to segment not just the big object, but also small object. And Alan's team also have invented the trans-UNet, also very popular, and people now have an UNet as well. So the idea of getting UNet plus is based on an observation that UNet in its standard version, it's a full layer of representation, but it may not be optimal for all size of the object that is a segment. So we did a very simple experiment. Different granularity of the object, the different level of the representation will be the optimal. So basically the issue is the standard UNet and its variance. We don't know the optimal depth of this architecture. So the natural idea is to just aggregate all this multi-scale feature within the UNet and ask the model itself to learn which is the best pace to segment the object of this data set. So two core innovation. One, we redesigned the skip connection within the UNet to make sure it's densely connected so the architecture can learn from the data set, learn from the object to decide what is the best. Second, we have a deep supervision that can allow the user to use any depth of the UNet in the inference time so that you can choose how big the model it is. And UNet++ very fast in this sense, because you can cut. It's a learn from the deep supervision. So in the inference, you can cut whatever you need. And the UNet++ have inspired a lot of different architecture design later on once it's published. And the UNet++ not only demonstrates the clinical impact, but also it was used beyond medicine. I heard it was used to detect something in the noon or something. Okay, so that's the architecture I want to highlight, and I continue to create more architecture like putting vision and the language together and so on. But the second challenge I want to say is even if you have a very wonderful architecture, the problem at the end is supervised learning. So you will have to get enough data to train your brilliant architecture. But in this case, you don't. Early stage cancer only have 10 or 20 less common compared with the late stage cancer scan. And this is exact kind of data that we want to collect, but in practice, it's not easy. And most early stage cancer, it's just hidden in the hospital database. You don't know there. So that's the motivation, say, can we synthesize very realistic but early stage cancer to train this AI model? Here is the idea. If we have a way to have the early stage cancer, then have this propagation to predict, to simulate how it will look like in the CT scan a long time, then from small to big. Then if we want to sample a lot of small tumor, we just need to pick up, stop in the middle and create a lot of small tumor for AI training. So that's basically the goal. And I call it a time machine. So you have a small tumor, you can become a bigger. Or if you have a big tumor, you can synthesize how it would look like when it's the early stage. Cool idea. We make it in 2 steps. First step, we want to simulate how this tumor and this surrounding environment would look like. We want to basically simulate the shape of the tumor and the organ. Second, we want to render how this shape will look like in the real CT domain. The first part, we use some algorithm called cellular automata. It's also called a life of game. It's basically a mathematical model that can use a very simple rule to simulate how things will develop a long time. Here's some example. You have a pixel of information and you have its neighborhood, and you can learn from its neighborhood to predict what's the next step. It's a very simple version as a word model nowadays, right? So you have a current state, you have a action, and you have a next state prediction. And in our case, it's specifically designed for cancer. So we have 3 very basic rules for simulating the shape. First is to simulate the growth, then invention to the surrounding area, and then the cell death. This is not enough. We also introduce a few biology rule, like when the cancer is getting bigger, it will push the boundary of the organ. And we also have a rule that the cancer be getting bigger, the duct will get dilated. It's getting pushed. And the water in the duct is stuck. So usually duct is not visible in the CT, but due to the early cancer, it's blocked there, it will become visible. So we try to model this in a biology way or the, if you will, the physical way. This is how it looks like. So we simulate not only the tumor, but also the vein, vessel, arteria, the duct, and the organ surrounded. And we simulate how it become bigger, and we simulate how it shrink along time. So that's a basic idea. That's an AI that can simulate cancer coming. And then it's a standard way to render. We use a standard diffusion model, or if in the future people have a better generative AI, we can use it. Basically, this is conditioned on the tumor type, tumor shape that the cellular automata give you, and then generate this realistic CT scan that you can train AI. Synthetic tumor is very useful. First advantage is it can help the AI detect very small tumor, because as said, AI need a lot of data to train, especially UNet++, you want to train this big parameter, you want to see this 0.001% of the information, you need the data to train it, otherwise it's overfitting. Then real world data cannot do it. And the synthetic data, you can inject as many synthetic data as you want to train. And here, of course, in the testing phase, we always use the real data to test. And we found using the synthetic data, you can improve the sensitivity of the AI in detecting small tumor by 5%. And the smallest tumor that we can detect is 2 millimeter. This is almost the limit of the CT resolution. 2 millimeter, it's a few pixels in the CT. If I tell you I can detect even smaller, that's a cheat, because that's become noisy, right? And the synthetic data can also reduce the bias. What I mean by bias in this slide is about a position. We know the tumor in the pancreas usually happen in the head of the pancreas. That means the data you collect have this bias, and when you test it, if the tumor on the tail or body, the AI will make mistake. Simply, it didn't see enough example. But if you got the synthetic data, if you have this error analysis, you know AI, in which case the AI will make a mistake. Then we can generate a lot of this kind of mistake sample to fine-tune this AI to improve the capability of learning, of doing these corner cases. Synthetic data also very good for domain transfer. This is a typical problem in AI, especially very important in medicine, because AI trained on Hopkins, it will fail very badly in California or other country. We have this test. So you are testing on Hopkins data, I will tell you almost 100% the performance. But when you test on Stanford data, oh my God, it's a 50. How to solve this? How to solve it? Usually people just need to do the talk to that hospital and give us more data. We annotate more and fine-tune this AI and do this kind of domain transfer. But if you have a synthetic tumor, the problem will be much easier, because to collect the cancer patient in the hospital is difficult, but to collect the normal patient, it's easy, relatively easy. So, and you don't need to annotate it, because you already know it's a normal patient. And what you do is you have this Hopkins patient with a very specific population, and you have a new hospital with a new population, new CT scanner, and you get a lot of normal patient, and you inject the synthetic data into it, synthetic tumor into it. So this tumor plus the normal version of the population will help the AI to learn this new domain of the information. So Now, finally, the AI can improve performance and do not cause a lot of burden of annotation. So this is a real result. It's not perfect, but I would say it's very encouraging. You have a Johns Hopkins Hospital performance almost 100% for everything. Then this is internal test. Then external test, we test on the California. We even test on Europe data and Asia data. We make a lot of friends to test all this kind of CT. Something I want to mention is this result from Poland. So this is third-party evaluation, and they are generous enough to give us the entire nation of the CT scan. It's taken either it's for cancer purpose or non-cancer purpose, whatever purpose. We really do a real-world test on this national database. And two note. One is our AI have never seen Poland data set at all. And second, it is a third-party evaluation. We never get the CT from Poland at all. We give the AI to them and they run it. And the direct quote is, okay, this AI is impressive. It can not just detect the large tumor very well, but also for the small tumor, for pre-cancer tumor, it also did a very good job. Question?
So first of all, it's great that this works. If you hadn't told us it worked, I would have been worried that when it tries to inject tumors on somebody who has a different shaped liver or something, that it might produce things that are actually out of distribution.
Yes.
And so I wonder if you had unlabeled data from Poland, could you use that to tune the synthetic data generator so that it matches marginal properties?
We can. Yes.
Something.
Yes, we can. We haven't been there, but it's possible because you can fine-tune this diffusion model because even the rendering part, different scanner have a different preference. So yeah, it's possible that we give them our diffusion model even to fit their image quality or something. Thank you. All right. So the last problem I sort of already partially solved it is that doing the annotation is extremely time consuming and it's a required expert. It's not an image that you can hire a high school student to do it. You have to, convince a very busy radiologist to help you do it. It's not easy. And why I worry about this, since I already have this good Hopkins data when I joined Hopkins. The reason is, by the way, we have this joint project called the Felix project. It's a collaboration between the computer science department and the radiology department. And this project already produced the very nice AI-ready dataset that radiologists give the per voxel contour for all the cancer and the surrounding structures. It's a very nice dataset. If you ask one radiologist to do it, this 5,000 CT scan will take 25 human years. And we ask many radiologists to do it. And finally, luckily, before I joined Hopkins, it's already ready. But I worried because it's a private data set. So many computer science people cannot benefit from it. Maybe only our team can work on it. Second, this data set is good, but it's only for pancreatic cancer. If I want to work on other type of cancer, I don't have all this resource to do this all again for several years. So that's the motivation I want to look into this problem. Yeah, two limitation here. Then I try to see the scaling law of this data set. Do we really need this large amount of data to solve one type of cancer detection? So instead of scaling up, like what computer vision people do, I scale these things down because we already have this data. I can do this simulation study to see what is the minimum requirement to train this AI that can achieve the performance I just tell you, right? So if you only use the real data, you randomly sample it, you only have almost half of the Felix data that can already get this performance. And if you have the synthetic data, the plateau will even go further and only 580% less annotation burden will be needed. So this is a really encouraging observation, because if I want to work on multiple type of cancer, it tells me the minimum requirement is there. It's a few hundred. It's good enough. And another observation is that once the performance reaches the plateau and the AI segmentation capability, it's very similar to radiologists. That means we can do bootstrap strategy. We don't need to bother radiologists to annotate the remaining of the data set. We can use the AI assist the radiologist to make this annotation much more faster. This is called active learning. I have been working on this since my PhD. It's also called human in the loop. So you start with this pre-trained AI model, and you test on all the unlabeled data set, and then you select the most important data, unlabeled data, for the expert to annotate. You give the priority. Why is that? Because a lot of data may be easy data that AI already make a good prediction, so you don't need to bother human at all. Then human annotate this small set of high priority data, put it into the annotated set. Then you fine tune this AI model on the newly annotated data. Then do this inference again, and you select the most important one again. So this important will be different from previous iteration because AI improved it, right? So the previous mistake, maybe AI can already fix it. Then you have this human in the loop question.
How do you select which data is important?
That is the next slide. So the people work on active learning, including me, ask the very question is how to select the most important picture. And I'm not going to go into detail in this talk, but we have this proof concept that, okay, you have this high entropy or high diversity kind of AI prediction, you want the radiologist to take a look. But in this talk, I want to emphasize another part of in this loop that's really important for annotating tumor, which is the AI inference. And I call it ROC analysis. This is how it works. So usually people want the AI to have a very balanced performance on the sensitivity, specificity, right, 90-90. But in this specific task to annotate the data set, you want the AI to be very, very sensitive to not miss any potential tumor, sensitivity almost 100%. Then this will give you a lot of false positive, right? But that's okay, because we have this software that if you create the annotation from scratch, the human will have to spend 4 to 5 minutes. That means, but if you find it's a false alert, if you remove the AI pseudo label, it will only take a human a few seconds, just one click, you can remove it. So that's why we want to make the AI to be overly sensitive to make sure all the possible tumor are annotated somewhat good, and then remove the false positive. Then the humans work, a majority of the work no longer create annotation. It's a majority work is to reduce the false positive, which is much easier. And in this pipeline, we find the AI can achieve this AI assist active learning can achieve almost 80% faster than you ask a human to annotate the database from scratch randomly. So with this active learning strategy, together with what I did previously for how to find the important scan, we are finally able to annotate all the public available data set in a fairly quick way. So you see the open domain, the cancer imaging data set is very, very small. That means smart people are not get a chance to work on this important problem. And we make this significantly change. So last year, use the active learning, we annotate 36,000 CT scan with cancer, without cancer, and we release it. It's from Johns Hopkins. And this number is it's in a different level of what is currently available in the public domain. So sounds like all good. So we have this successful story. We have an AI strategy to get a very good architecture to detect small tumor. We have image synthesis to get enough data to train on, and we have active learning to make sure this annotation goes very fast, and we can quickly build the AI-ready dataset. Everything goes really well, and I'm ready to move on to the multi-cancer detection, go beyond the pancreas. And my career goal would be, okay, we spend 4 years or maybe even longer year to finally make the proof of concept on the pancreas. And now we may spend less year to work on other cancer and do this step by step, right? And the NIH also really liked our preliminary result on pancreas study, so they agreed to give us $2.5 million for 4 years to work on this colon cancer as a starting. And my career goal is to really work on it one by one. But you know what? Research always not linear. It's always give you some surprising moment that can make the story entirely different. That happened luckily last year. Once we get the NIH funding, we find a way that can quickly make the 7 type of tumor reach or even outperform human expert in a very quick time. So I call it a aha moment in my research career. And what is happening? Because we find that AI can actually benefit a lot from the paired image report data. And all these data are already available in all hospitals, just whether it's curated already or it's not curated, it's already there. And the report was there because the radiologist's daily work duty is to write a report. But the hospital, they do not have the AI solution that can exploit this huge amount of image report pair. Here is a screenshot of a more successful story that I'm talking about, 7 different type of new cancer. And you never see this performance in the public domain because there's no public data set that allow people to work on this. And that's why I don't have any baseline here. It's different from CVPR. I usually have a lot of baseline. This is a brand new problem. And the only baseline we can have is the human performance. So we ask a group of human experts to look at all these type of tumor in the CT scan and give us their performance. And the gold standard is it's a surgical validation. So that's why the human is not very good. And you see, from at least all these 7 type of tumor, our AI can already achieve a very similar performance or sometimes outperform them. And my previous statement not entirely true because we know there are a lot of foundation model from the big company, and some of them are working on healthcare as well. So we also because there's no public data set, so no specific model are trained on this cancer. But what we can do is bring all this foundation model. They said they can do zero-shot learning. They can do all this type of cancer. Then let's try. So here is the result. The AU's ROC 0.5 is almost a random guess. That means the foundation model not really work at this moment for all this multi-cancer problem. So the aha moment is really the observation that we rethink our strategy, say, do we really need per voxel annotation to train AI to solve this multi-cancer problem step by step, or we can use something more smarter, right? So here, writing report is part of the standard workflow, but giving per voxel annotation is not their standard workflow, and they hate it. So that's why I feel like what I presented before, active learning is wonderful. It's 80%, it's 80 times faster. It's still not good enough because it will spend me another decade to finally work on 3 type of or 4 type of cancer. It's still not good enough. It's not scalable to multiple cancer. But what I present is actually very useful because what we released, the 36,000 annotated per voxel annotated CT scan, have attracted a lot of collaborators around the world to help us building this. So they know there's a team at Hopkins. They are working very actively to do the AI-ready dataset curation and the release. So we get this reputation that give us the opportunity to work on this huge amount of CT scan from different countries. So far we get 2.5 million CT scan. We have access to it from 445 hospitals worldwide. And this is very important because these CT scan are taken from different population, different scanner. It's useful for at least testing AI. It's also useful for training AI. And we also build a very close relationship with a major hospital within the US, including Johns Hopkins, Harvard, Northwestern, Stanford, and UCSF. And all the good aha moments start with the UCSF because they want us to build even better algorithm to use their data image, their huge amount of data. And even outside the US, we also get a very good partnership within the Canada, the Europe, and the Asia. So this really allow us to do this aha moment. Why is that? Because they are willing to open their whole hospital database to us. And we can finally analyze what is the full potential of radiology report. This is the histogram that we use LLM to automatically read all these millions of image report. We read this report to summarize. Then I finally realized, oh, there are hundreds type of cancer that I should work on. I may not even finish it my entire life if I just stuck with my old approaches. And most of them are in a long tail. So radiology report is really make this possible. Because if you want to only work on one type of cancer, you can ask them to annotate. But if you want to work on hundreds of annotation, they will refuse, definitely. And the radiology report, why it's good? Because when the doctor look at your CT scan, it's not just focused on one organ. It will focus on all the organs that is present and write down whatever it observed. So that's why the report itself is naturally a very good enabler for us to do the multi-cancer detection. Then we come to the topic of vision language, because the computer vision people also have a lot of work to use the image and the report pair to learn this kind of a foundation model to learn the semantic alignment between the image and the text, and whether we can use it directly without any change, right? That would be nice. So the most famous work is called CLIP. It basically train two encoder. One is train a text encoder, and the second train an image encoder. And you make this text and image. If it's a paired text image, then you make them closer in the representation. If it's not paired, you make it far away. And here, pair or not pair, they use the automatic way to download from social media. So you assume that the image and the text is automatically paired in the social media. But we found a problem. It's not necessarily true. Because in social media, you can post the image, but the text is entirely not really explain this image at all. So this is my example. When I give a talk in the ICCV, the Hawaii morning is really beautiful. I take a picture. I'm really looking forward to my talk. So it's not relevant. And I also want to remind everybody the text and the image not necessarily pair in the social media. But in medical domain, it's different. Because writing this report, it's doctor's job. They are paid for it, and they should be responsible to it. And this report should be as detailed as possible. So that's open another opportunity that this report is trustworthy. And if we have a way to extract the extract the information from this report and use it to supervise this this learning process, that would be really nice. And the second problem of a conventional VLM is that they assume you want to align the feature with image and feature with report. That's okay for the natural image because in the natural image, the object of interest is very big and you can naturally align them together, no problem. But in CT scan 3D, I said 0.0001. How can you learn this contrast learning with only this bit of information that is relevant to what is written in the report? It's not easy. And it's really motivate us to really do our own job to create something that is really useful in medical domain. And we designed this AI algorithm that can learn segmentation from the text in the report. And I guess the community really like it, and we get the best paper award runner-up last year for the MICAI community. What it did is quite straightforward because I said the report is very detailed and it gives you the information how many tumor there is and what's the size of the tumor and what's the rough location. And we can find a way to use this information. So we have a two model. One is the language model to learn from this report to extract all this information as a structured version. Okay, location, if it's mentioned or not, if mentioned, what it is. If it's size, what it is. What the number of tumor, what it is. And then we use this structured information to supervise the segmentation model. So we have another model to analyze the CT scan and give the pseudo tumor prediction. And we try to design this loss function to match this tumor pseudo prediction with what is written in the report. It's very simple. So if the pseudo mask is like 2 centimeters, but the report said it's 5 centimeters, then you give a penalty. Otherwise, you don't. So with this, we are finally able to create this huge amount of image report pair and a limited amount of image mask pair to see what we can do for the multi-cancer detection. And again, there's no public data for enabling this kind of research. And we released the first AI model can finally segment this 7 type of cancer that is reach almost the radiologist performance, which lead to the results I give to you before. And the question?
Question on this point. I guess there's a specific question, a general question. The specific question would be when we're doing this feedback on the segmentation, it sort of makes sense in the context where the radiology report contains mention of the size and you've segmented something of that size. I guess, do you have cases where you've segmented something, but then the report doesn't mention a tumor, and so you say, yes, okay, maybe I was wrong? And that's a specific question. The general question is, you have these results around how radiologists miss a lot of things. And here you're using radiology reports as kind of a ground truth. So I'm sort of curious how you think about the tension between those.
It is not good because radiology report cannot be used as ground truth. So that's, in another word, it's a noisy labeled data set, but it's still good enough to ask AI to learn something like obvious. If the radiologist missed it somewhat, then yeah, this is a wrong label, that's for sure. It's also happened in the per voxel annotation. This also happened, right? So if the human missed it, it will not give you a per voxel annotation. So that's the story is consistent, and the AI trained on some easy data, and we tested the AI on the hard data that missed by that radiologists make mistake. But all this result I present, it's validated by the surgical outcome.
Thanks. So useful for training.
Yes. Yes. Otherwise, if we just consider radiologists as a gold standard, it's never, never can help them. Sounds like. All right. Question?
The 270 mask pairs, were they like how many cancers were included in that? Because obviously if you're working on.
So far, we are working on 10 types of cancer. I only tell you 7 because other 3 are not good for many reasons. We are still working on that. So yeah. And yeah, we're not working on hundreds of cancer now. We are find the top 10 that are most impactful ones.
So be what, 27 images per? Feel like, wow, so little.
Yeah, about this small amount of image mask pair, I will present in the next slides. It's not only done by the active learning I present to you, we also use the report because with aha moment is a report so wonderful, right? So we use the report to even enhance my active learning that, okay, so previously we adjusted the threshold of the AI prediction to give a very high sensitivity. It's a threshold that's applied to the whole image. But now, since we have a report, we know there's a tumor in this size. Then we can apply the threshold on this local region. So the AI prediction can, meet this what is described in the report. So for example, you have this 0.5 threshold, it gives you 2 dots. But if you say report tell you have a 1.6 centimeter tumor there, then you can make the threshold a little bit lower to make these 2 dots combine each other, then become a quite nice segmentation that the human can edit. So that's a little bit tricky trick that we do to make this even faster. Report is wonderful for another reason because as said, the report can give you the information of all cancer. It can also give you the information about the multi-disease. And you know that when we test the AI, it gives you very good specificity. That's because probably our test set is not big enough. But if you continue to analyze the error case, you will see the AI make a mistake, make this false alert, usually happen when this patient have a non-cancer disease. For example, we get a histogram of this false positive that we get. The number 1 is the atrophy of the organ. So it's an early sign of the cancer, but it's not really cancer. And we also have other reasons that make the AI confused with the cancer. And we have the report to automatically analyze this error. It's not easy because some of this non-cancer disease prevalence even smaller than cancer itself. So that means you have a very little chance to know this kind of error unless you have a very systematic analysis on this. For example, pancreatitis, the prevalence is much lower than pancreas tumor. And we can use this result to do the hard negative mining to include this. Okay, we know AI make a mistake on this, then we use this additional data to tune the AI to make it even better, less false positive. And we also improve our vision language model to do the report generation. So as said, there are standard way to do report generation. It's end-to-end, you got the image in and you get the report out. That's what most people do. And what we developed is to report this image grounded on the segmentation representation. Why this happened? So this is a conventional what people do, a very big model trained on huge amount of image report data. And it's end-to-end, it's give you hallucination, it give you the report that look like a human written, but the key information are completely wrong. And what we propose is to have a 2-stage. First, you have this model to analyze this image and give the representation, how this tumor look like, how the environment, the vein artery look like, and where it is within the within its organ, and how it look like in the whole body, and then write this report. And we compare our approach with the standard VLM It's all this VOM is developed for medical purpose. Merlin is just published in Nature weeks ago. And we tested this report generation model on tumor detection task. And we found it's all these existing model almost cannot do this task at all. You can see they have a very big specificity, but zero sensitivity, meaning they have no idea what is going on. But if you can report based on the semantic segmentation, it can make your problem much easier because the hard part is to understand the human anatomy. You can summarize this representation in a way of a semantic segmentation. You can also summarize it in a JSON, like a structured representation or bounding box. You can summarize all this representation in a way that LLM can be able to analyze it, or other deterministic algorithm can analyze it. So you have this segmentation, you can report how big the tumor is. It's quite easy. And I also want to add one more component to this graph, is that in order to train this first step, you can even use the report. You can bring the report back to do the supervision. So you make this loop, this into a positive loop that a report help semantic segmentation, then help reporting. So that's what we change for the VOM thing. Okay, to sum up, my talk I have two chapters. First, the chapter is focused on one type of cancer. We have this development and works very well. I have a very good career plan to work on it one by one, like in a very good way. And I also get NIH funded. I'm planning to get more type of cancer submitted to NIH. But in chapter 2, I really talk about something that we can quickly make a good result in some type of cancer quickly by exploit the information from the report, and we can even help the radiologist to write a report, because segmentation is not a radiologist's final goal. What they want AI to do is do reporting. And I think in the similar strategy, we can use a report to make more future story, like make the multi-disease happening. So here I also use a language model to analyze this report. The top of 500 different diseases are in the report. And finally, I'm thinking how to make this AI really useful in clinical setting. So what I report, the result is pretty good, but it cannot be used in the clinic at the moment. Why is that? I want to introduce a concept called PPV. PPV is different from sensitivity in a sense. PPV means if the model thinks it's a tumor, how many chances it is a tumor. Sensitivity is that if there's a tumor, how many times the model can pick this up. So they are similar, but quite different. So finding a tumor in the general population is like find a needle in the haystack. So let's say the prevalence of the cancer in general population 0.01, 100 out of 1 million. And usually a paper will report the very nice sensitivity specificity. I said the JHU AI is very nice, but most paper, they will not tell you their PPV because it's very low. So if you use 95, 99 sensitivity specificity, you will get a PPV less than 1%. That means if the AI thinks this is a tumor, only 1% of the time is correct. Why is that? Because the AI can find a 95% correct, but it will, because the specificity 99%, it have a 1% of chance it give you false alert. That is 10,000 false alert. If you do the PPV calculation, less than 1%. The solution is really to apply our AI model to the high-risk population, where the prevalence it's increased to 4%. So give you the same sensitivity specificity. Now the PPV can reach to 80%. Our algorithm can reach 80%. Means if our algorithm thinks there's a cancer, 80% of them are correct. That is pretty good, because if you take a look at the FDA cleared software for breast cancer screening, the PPV is only 20 to 40%, depends on which population you are tested on. So the 60% PPB is very good already. So this leads to the several ongoing work I'm doing. I'm not just to do the AI that can see the cancer coming. I also want when the cancer is not there, we want this AI to forecast the cancer. That go back to the problem. How can you develop this risk model that can use the risk factor from the health EHR and get the image biomarker from the image. And you can also benefit from the multi-modality image. And we have this preliminary study to combine all these Q together, risk factor and the image biomarker, to predict the high-risk population. Second, we want to, once we detect it, that's not the end of the world. We want to cure it. So I also want to build this AI that can treat cancer. So I work very closely with the Department of Radiation Oncology professors, and we try to make sure the radiotherapy planning can be benefit from our semantic segmentation, because all they care is how to destroy this cancer region while make other healthy part unchanged. And this require very good semantic segmentation, and it's also need a predictive model that can predict what is the response of the treatment. And third, I want to have this AI to make a CT more safer. So now you think about it, how many of you have a CT scan in your life? Not many, right? Okay, so the problem is that we have this wonderful AI algorithm, but not many people can benefit from it. But at the beginning, you need to convince them to do CT scan. And the CT scan, first you need to find this high-risk population. Second, the CT scan is dangerous. It have a radiation. So you also want to use AI algorithm to extract more information, but use less radiation. So we have we have submitted an NIH grant on this to use two strategies. One is a sparse view reconstruction, and the second is to do the image enhancement to create a very high quality CT scan, but with a very limited amount of radiation dose. So in general, I want to try to build this called cancer world model. It's a predictive model. It's not just to work on the current time point. It also can predict what this cancer will be and predict why this cancer begin. And also, this cannot stop in the image only. It should do the treatment as well. And ideally, this solution has the input of the disease patient and output of a very healthy patient. So my research is focused on two parts. One is to do a lot of algorithm design. I introduce a lot in this talk. And the second, I really don't want this algorithm just to be novel. It should be working in the real world problem. So I work very closely to the clinical application. In this talk, I talk mainly about the early cancer detection. I also do the radiotherapy planning and the treatment response and the report generation. And here's some good thing about me. And yeah, our lab it's just started. I have one postdoc and two PhD students, and we are open to the many students for the summer internship and to work with us. I hope my talk interests you to work on this problem. And we also have a body map demonstration award. If some of you brilliant enough, you can solve this multi-cancer problem. Not all problem, just make some type of cancer that are good enough compared with the radiologists. We make sure it's useful for the radiologists. We have this kind of award for you. Okay, that's all I prepare for today. Thank you very much.